chemistry friends. Today what we're going to be doing is focusing on a laboratory technique that's called a titration. It's probably a good idea if you get the definition down of what a titration is in your notes. And in essence, what we do with the titration is we perform a laboratory technique which allows us to determine the concentration of an unknown solution if we know what the concentration of another given solution is. And again, in this titration, we will be collecting some lab data, and then from this data, we are going to be able to do some calculations to, again, determine the concentration of an unknown solution, knowing what the concentration of a given solution is. So the idea of doing a titration in our acid-base unit is based on the concept that acids will neutralize bases and also bases will neutralize acids. When we think about this in terms of a real world, let's say we were out on a nature hike. Uh-oh, here comes a bee, a wasp. Well, it turns out that when a wasp stings you, he stings with a base. That's the venom that he injects you with when he stings you. So if we want to neutralize that venom and it's a base, what we're going to do, I think you guys all understand what we need to do is we need to neutralize it with an acid. In this case, you might want to use some lemon juice, maybe some vinegar. That would then hopefully neutralize the base and make that painful wasp sting a little less painful. Yay! On the other hand, if we get stung by a red ant, certain red ants, when they bite you, they bite with an acid, and as I'm guessing most of you understand right now, what we need to do to counteract that venom is we need to use a base, and baking soda is a base. So you maybe have seen times when maybe your mom or friends' moms have packed like a baking soda paste on top of a particular bug bite. The reason being, again, is that if the bug bit you with an acid venom, then the baking soda should help neutralize that and make the pain not so painful. And then we're all living happily ever after. So the idea of acids and bases neutralizing each other, we use that idea in our titrations. And you may recall that when you mix an acid with a base, it's a neutralization reaction, double replacement reaction, where the products are a salt and water. Now when I say salt, I don't mean sodium chloride in all cases. A salt is going to be an ionic compound where it doesn't have hydrogen as the cation or hydroxide as the base. An example would be HCl, which is our acid, sodium hydroxide, which is our base. And you'll see in a double replacement reaction, we make our sodium chloride, which is our salt, and hydrogen hydroxide, which we also call water. You see how the cation switch places? That's what we get there, a salt and water. So what happens if we have an upset stomach? Okay, what we want to do is we want to take an antacid or an antacid. That will make us feel a lot better. Here's a case where we've got our hydrochloric acid, which is the acid in our stomach, and it's going to react with the active ingredient in our Maalox, which happens to be magnesium hydroxide, and then you can see what we get as our products then would be magnesium chloride and 2 water molecules after we balance the equation. So let me ask you this question. If 1 mole of hydrochloric acid is in the presence of 1 mole of sodium hydroxide, okay, we know a neutral solution is made. If we have 2 moles of hydrochloric acid reacting with 1 mole of magnesium hydroxide, we get our magnesium chloride and 2 moles of water. So what is the molar ratio between this acid and this base to produce a neutral solution? Now remember, in our HCl sodium hydroxide situation, for every 1 mole of HCl, we needed 1 mole of sodium hydroxide. In this case, for every 2 moles of hydrochloric acid, we need 1 mole of magnesium hydroxide. So we're going to be using these molar ratios, doing a little bit of stoichiometry to help us determine unknown concentrations. Well, how is it you know when you've actually neutralized an acid? You can mix two things together. How do you know that it's actually neutral? Well, what we're going to be doing is we're going to be using an indicator. We're going to be using phenolphthalein. As a reminder, we learned this in our first lab of the unit, phenolphthalein is going to be clear in an acid. Here's a picture of a flask that has an acid in it, and if phenolphthalein was put in it, maybe 2 or 3 drops, it would remain clear and colorless. On the other hand, if we add phenolphthalein to a solution in a flask where we have a base in the flask, we're going to get a magenta color. The deeper the magenta is, the more base that we have there. So what color will this phenolphthalein be then if it's not an acid or a base? It's actually going to be halfway in between the two, not clear, not magenta. It's going to be just a hint of pink. And that's one of the first issues we are going to be having in our titration, is we are going to be mixing our acid and base together in the presence of phenolphthalein, and we're going to need to do it very, very carefully, drop by drop, so that we get just a hint of pink when we do that. So let's do a quick question right here with your partner. What color will the phenolphthalein be if it's placed into an HCl solution? Ask your partner real quick, make a decision. Did you say clear? Nice job. HCl is an acid, so it will be clear. How about H3PO4? Do you remember that that's called phosphoric acid? It's an acid, so again, that one is going to be clear. Calcium hydroxide, notice that it ends with the hydroxide ion. That's one of our hints. If we put hydroxide ions into solution, we know it's a base. Therefore, if we put phenolphthalein into this, we will be a bright magenta. All right, as a reminder, we already wrote down this definition in your notes. Titration is a laboratory technique, and it's performed to determine a concentration. In this case, we're going to be talking about the molarity. And what we can do is, if we have a known molarity of an acid, we can figure out what the molarity of a base is, or vice versa. Alternatively, we can also determine the volume of any particular acid or base that we might need to neutralize another if we know their concentrations. Both of these two situations we'll be able to do with the data collected from a titration. So let's try an example here. Let's say we had a 2.1 molar magnesium hydroxide solution, and we decided we used 23.9 milliliters of that. And we used that to titrate, meaning to get to that hint of pink, to a neutral solution, using an aqueous nitric acid solution, and we determined we need 15.21 milliliters of that nitric acid. Well, this information is enough to help us to determine what the molarity of the nitric acid is. In a pictorial view, again, here's my acid, my 15.21 mils of it. I don't know what its concentration is. It's going to be clear in the presence of the phenolphthalein. My base, my 2.1 molar, 23.9 milliliters of it, is going to be magenta in color. When I mix the two of them together, I will be neutral. I will be at that just hint of pink. And again, I'm calling my nitric acid my unknown. It's unknown because I don't know its concentration. I'm going to call my base my known because not only do I know its concentration, I also know what volume of it I used. So I know both of those pieces of information. So we do have 4 main steps here for calculating concentrations of a titration. And we need to be, first of all, making sure that we write that complete balanced chemical equation. And you guys know me well enough that you better include those states of matter. Then what we're going to do for our known, that's the one where, again, we know both the volume and the molarity. What we're going to do is we're going to solve for moles of the known. And we're going to do that. We learned how to do this in our water unit. If we know molarity equals moles over liter, if I plug in the molarity and I plug in the volume in liters, just do some algebra to figure out my moles of the known. Then, because I know moles of my known and I've got a balanced equation, what I can do is use stoichiometry, and I can calculate how many moles of the unknown must have been added. And then at the end, I'm going to then be able to figure out my concentration, or volume if that's what I'm asked for, using again the molarity equation. So let's go ahead and let's try an example using these 4 steps. Again, balanced chemical equation, solve for moles of the known using the molarity equation, solve for moles of the unknown using stoichiometry, and then solve for the final missing information of the unknown using the molarity equation once again. Okay, so let's say for this problem that we did previously, we know we've had a nitric acid and magnesium hydroxide. So why don't you guys go ahead and write the complete balanced equation for that. I'm going to pause momentarily to give you an opportunity to do that. Don't forget your states of matter. Okay, is this what you got? Did you get that you needed a coefficient of 2 in front of the nitric acid, state of matter aqueous, with no coefficient or the understood coefficient of 1 in front of the magnesium hydroxide aqueous? Now I used an equal sign here. Know that I didn't mean to use that yield arrow. 2 moles of my HOH, which is water, which is a liquid, and then the 1 mole of magnesium nitrate. All right, that was step number 1. Now step number 2 is where I need to use the known piece of information to solve for moles of the known. Now we'd said previously that the known information in this case was my magnesium hydroxide because I both knew its volume and I knew its molarity. So we are using 23.9 milliliters and it's 2.1 molar. Please, please be careful on this one. Remember, we use milliliter quantities in the lab, but in our molarity equation, we need to first convert it into liters. So I'm going to go ahead and pause again and let you go ahead and set up the molarity equation. Remember, molarity equals moles over liters. Watch your sig figs when you're done as well. Alright, so what I got for this is I got that moles equals moles over liter, molarity, equals moles over liters. So I plugged in the 2.1 molar as the molarity and I converted my milliliters into liters, did some algebra, and what I determined here is that when I added 23.9 milliliters of my 2.1 molar magnesium hydroxide, what I was really doing was adding 0.050 moles of magnesium hydroxide. Okay, so you'll recall the third step is to do stoichiometry. We're going to solve for the moles of the unknown using the moles of the known. So I'm going to start my T-chart with what I just solved for, the 0.050 moles of magnesium hydroxide. And then I'll know the molar ratio from the balanced equation that we did up in step 1 there. And then we'll just go ahead and we'll solve for that. I'm going to pause here, let you see if you can do that with your partner. Remember, you're starting the T-chart with your 0.050 moles of magnesium hydroxide. And then to convert from moles of acid to moles of base, what you're going to do is you're going to use the coefficients from your balanced equation. So you get something that looks like this, and then what you figured out is that what you've done is when you've mixed those two quantities together and made a neutral solution, you've added 0.10 moles of nitric acid. Now remember, our purpose here is to figure out what the molarity of that nitric acid is. If molarity equals moles over liters, the problem told us how many milliliters of nitric acid we needed. We just solved for the number of moles, so now we just simply have to solve for the molarity using the molarity equation again. Why don't you try that? Remember, you're using the moles of nitric acid that you just solved for in step 3 and you're using the volume based on what was given to you in the problem, remembering, of course, to convert it into liters. So when you do that, what we end up here with is the nitric acid must have been 6.6 molar. Now when you do this, please be careful. Notice up here in step 2, when I did my 0.050 moles of magnesium hydroxide, I actually indicated that it was magnesium hydroxide. When I solved for my moles of my acid, I indicated that it was moles of acid. You just want to really be careful with this just to make sure that whenever you're doing a molarity, you're grabbing the correct moles, whether you're solving for your acid or whether you're solving for your base. Okay, now what it's time for you to do is it's time for you to work on your problems in your packet.